Welcome. We're going to go over the basics of probability, very much like how we went over the basics of combinatorics. So I'm going to go through some basic examples and work through them. When I present them, I want you to pause the video and try them yourself. Most of this should feel like it's review based on the things you've already done in your discrete math class prior to this, as that is one of the outcomes of discrete math is discrete probability. So we're going to get into this. We're going to apply discrete probability. We're not doing continuous probability. That's more of a calculus based because we're going to do this in discrete situations. So let's look at a first option. First question, what's the probability of rolling a 2 with a fair six-sided dice? So some of our options we're going to do are going to involve, just like we did combinatorics, are going to involve dice and cards. These because they're very simple examples. Normally, if this is a classroom, I would literally pull out a dice and we would roll it. So the question is, what's the probability of rolling this? Well, remember, probability in general, going back to your discrete math classes, probability, a way to think about it is the number of desired outcomes over the number of total outcomes. So these are everything that's possible, and this is the ones that I want that are possible. So the probability of this, well, if I'm rolling a six-sided dice, how many ways can I roll a 2? There's only one way to do that because, well, that means the dice shows a 2 on it. But if it's truly a fair-sided dice, there is six outcomes: 1, 2, 3, 4, 5, 6. So that means I could have gotten a 1 in 6, or approximately 16%, if you want to change this to percentage. This is about of rolling a 2. Well, what if I change it just so slightly? Instead of saying what's probability of rolling a 2, what if I say what's probability of rolling a 3? Does it really change it? You're saying no. Because the truth is, each of these outcomes should have equal probability of happening. That is what the definition of random really means. So when we're choosing a random number, for instance, you're really setting up essentially a dice roll in a computer and having it ran and have them pick a value. Each value has equal opportunity to occur. So this is still 1 in 6. I'm not going to even write it down, but let's change it a little bit and say, what's the probability of rolling an even number? So let's step it up. So first I did a 2, and then I did a 3, and now I did even numbers in general. Well, again, I'm rolling a six-sided dice. So, and again, you can pause this and try this on your own. But when you think about it, here's the question. The probability of even, how many total and how many even options are there? Well, there would be 3 even options, namely 2, 4, and 6. Change that to a set. In totality, there's 6 of them. Or we could write 1 and 1/2. The probability is 1/2, which is 50%. So we have a 1 in 2 chance of rolling an even number. Does that mean that if I roll the dice twice, that I'm guaranteed to get an even number? The answer to that is no, because even though probability says I should, there is still a chance that I could roll the dice even 5 times in a row and have it all be odd numbers. And it still technically is a fair set of dice, just because each number has an equal probability of happening. And so things could happen. The likelihood of that specific scenario, we will actually get to that a little bit later on and talk about that a little bit more. All right, so let's stop dice and let's go to an alphabet soup situation. So I have a bowl, it has 100 letters in it that are from the alphabet. 14 of them are A's, 23 are B's, 45 are C's, 18 are D's. If I draw a letter from the dish, so I'm taking my spoon, I'm pulling just one letter, what is the probability that letter is a C? What is the probability it's a A or a D? What is the probability it's not a B? So go ahead and pause the video, try answering these questions on your own. All right. So again, let's just break them out. Let's talk about the probability of a C. So our first one, this is where this gets actually quite interesting. Probability of C is equal to, well, it's out of 100 because I have 100 letters. How many C's? I have 45 C's. So it's this, and we could reduce this if we want to 9 out of 20. It doesn't matter. This 45 out of 100 is perfect because it actually tells us this is 45%. It's really easy to do percentages when you're doing something out of 100, as that's what percentage means. All right, so C, that seemed to be pretty straightforward. What of our second question, which was what's the probability of an A or a D? Well, what we can do is how we still have out of 100. Well, how many A's do I have? I have 14 A's and I have 18 D's. So I have 14 plus 18, which equals 32 out of 100. Or again, you can reduce this and get 8 out of 25. Now, I will note something real quickly. This is equal to 14 out of 100. What we know about fractions plus 18 out of 100, which is equal to the probability of A plus the probability of D. And the reason we can do that is because it's an or. There's actually two reasons we can do this. It's or, and A's and D's are disjoint. They have nothing in common. So we need a disjoint situation to be able to actually leverage that and use that to our advantage. Otherwise, there's no guarantee of that scenario playing out. All right, last but not least, what is the probability of not drawing a B? So again, I'm just going to write this down using the logic symbols. Probability of not a B is going to be out of 100. Now, I could have done this out of 100, and I could have written down what are all the other ones. Well, A's, I mean, has to be 14. No B's, skip the other one to 45 plus 18. So this is A's, C's, and D's. And quickly add all those together, and guess what? That adds up to 77 out of 100. Quickly, interesting enough, this is equal to 1 minus 23 out of 100. And the reason I bring that up is because this value right here, 23 out of 100, is the probability of B. So the probability of not doing something is equal to 1 minus the probability that it does occur, because probability has to be equal in total equals 1 or 100%. The total probability of all the scenarios has to equal 100%. So we can do again, look at what we don't need, 1 minus what I don't need, and it gives me what I actually do want. So by looking at complements and things like this, we actually get to leverage this super well. All right, let's look at our next one, which we're going to switch from an alphabet soup to an alphabet box. So I have 26 cards in my box. There's a letter, each has a letter of the Roman alphabet on it. I apologize. I apparently mistyped it and have a letter twice. What's probably selecting a pair with, so I'm going to pull out two cards, one with an A and one with a Z. Well, again, remember probability is about what do I want? So there's two ways to do this. I could talk about what is the probability A and Z. We'll have 26 cards. Well, the first one, I have one card out of 26. And the second card, so this is the probability of drawing an A. But if I draw an A out, there's only 25 cards left, and only one has a Z. So I could do this. This is probability of a Z after an A. Because if I've drawn the Z out, then that's kind of given. Well, this is kind of a strange, kind of hard situation we're kind of stuck in. We're sitting here going, how do I mean, obviously we multiply this. However, this is assuming that I drew the A first and then I drew the Z. Could I have done the other way around and it would have had the exact same probability. So it turns out this is actually equal to 2. I multiply times 2, which is going to be 2 over 26 times 25. And I won't bother doing the calculations, but again, we get this. But is there a different way to have done the same problem? A different question would have been this. How many ways are there to draw a pair of cards out of here? Well, we have 26 possible cards and we're pulling out 2. Order doesn't really matter, so that would be the binomial option. And only one of those pairs we want. Interesting enough, this is 1 over, and then 26 choose 2 is taken back to the formula, 26 factorial over 24 factorial times 2 factorial, which equals 1 over 26 times 25 over 2 factorial, which is 2 times 1. And remember, when you divide by something, you flip it. So that's equal to 2 times 1 over 26 times 25. Wait a minute. This and this are the same. So we could have done this, again, by knowing how to count. We actually realize that we're counting, instead of counting the different situations, I'm just saying, how many ways could I have drawn 2 of them out? Well, there were 26 choose 2 ways to do that. And I only want one exact situation. Now, this is important because it helps us out with the very next question. I'm going to go ahead and clear this. And that is, what is the probability of selecting a pair of letters that are adjacent in the usual ordering of letters? What I mean by that is pulling out an AB, BC, CD, etc. Not an AZ, because that's not usually considered adjacent. Y is adjacent to Z, but not A. So with that in mind, go ahead and pause the video and answer this question based on how we answered the first one. Okay, so if you come back and you think about that one, the probability of adjacent pairs still have 26 choose 2 because I'm pulling out 2 cards. Really don't care about the order that I pull them out. And that's part of the reason that we're actually playing this to our advantage. Because I pull out 2 cards, I'm just saying they're out. Now, if I actually put a specific ordering on them, this 26 choose 2 actually then fails, and we got some issues to go. But let's just stick with the fact that we haven't said the ordering doesn't really matter. So I'm selecting a pair of letters. Well, that means how many ways could I have done that? Well, I could have picked AB. That's one pair. I could have picked, actually, I'm just going to write a list of them. The next one that I could have picked would have obviously been BC, CD, DE, all the way up to YZ. Wait, so this is how these are the adjacent pairs. Now notice, how many adjacent pairs do we have? We have 25 of them. And the reason we have 25 is because we have A is leading A, B, C, D all up to Y, but not including Z. So one less than 26. So hence we have 25. Boom. All right. This is where understanding these concepts is way more powerful than just trying to pick some specific formula. This is all about trying to think, if I'm picking pairs of things, well, I can use my binomial coefficient to my advantage here and kind of use those things to kind of compute this. Let's do a similar kind of thing. But let's say there are 20 A's and I have 20 B's in a container. So again, it's kind of the alphabet soup, but all I have is A's and B's. If we select a pair of letters from the container, what's the probability that both letters are A's? What's the probability that both letters are B's? And what's the probability that they are different? Go ahead and find that answer and unpause the video. All right, so if you do this, let's just break this down into the three different options. We want to find probability, I'll call it AA. We want to find probability of BB. And the last one is probability of AB or BA. Because remember, order, I mean, it depends on how you want to consider it. Well, the nice part about this one is how many ways can I pick? I have a total of 50 things. I'm picking pairs. So that's going to be 50, choose two. From there, I can say, well, how many ways are the pick two A's? Well, that's going to be 20, choose two. This one would be almost identical. So this will be 50, choose two in the denominator, and then numerator B, 30, choose two. That's excellent. And the bottom one would be 50, choose two. And no, wait, how do I do the top? Well, the number of ways to get A and B, if you think about it, each of the A's, I could have 20 A's. I could have an A followed by a B or a B followed by an A. So this one actually is a little bit harder to write out this way. But because I would normally think about this and write it down and be like, okay, this is actually going to be 30 times 20 times 2. And where you might ask about why the times 2. Well, this is if I pick a B first and then I pick an A. But what if I picked an A and then picked a B? That would change the ordering of it. And so I can have double the number of ways to do it for each of these single situations. So because I have 30 different B's to pick from, and each one of those could have gotten 20 A's. And similarly, I could have done. Now, another way to have done the same exact thing right here would have literally been this. I could have instead written this as we could have instead worked our way through it and kind of thought, well, how many ways can I choose them? I'm choosing one A and choosing one B, and we're leveraging them from that standpoint, which still kind of gets us to that point in time. So let me know what questions are. Wait, I'm not done. I don't know why I started even saying that. So this is where this is going to get kind of tricky. Is there's not one just kind of fix all kind of idea. Let's go back to the die situation. Except now I'm going to give you two dice. I'm going to call one red and one blue. If I make them different, what's the probability that one red die is odd and one blue die is 4? The nice part is they're almost fixed. Because they're fixed, it's almost like saying I have an ordering. So instead of saying dice, it's almost like I'm saying I have a sequence of numbers or sequence of values. And this one is odd from, wow, that's not a form, from 6. And this one is a 4. Well, there's only one way to depict the number 4 on the blue die. The red die, if it's truly a six-sided die, we've already established there are 3 out of 6 options here. And I should say instead of 1, it's 1 out of 6. Because each of the first 6 options, so I could have done 3 and 1 and gotten 3 times 1 over how many ways do you have 2 dice? And that would be 6 times 6. Or I can have 3/6, number of ways to have odd, times 1/6, number of ways for the second one to be odd. So when we have this ordering, it's super easy to be like, I'm gonna roll the red dice. What's the probability it gets odd? Times what's the probability the second one is 4? And we can have our answer, which is 3 out of 36 or 1/12. Or what if we now say the 2 dice are identical? They look the same, so I can't tell the difference. What's the probability one is odd and one is 4? Now, your instinct might be like, let's just go with the same answer, which is 3 out of 36. And if you just went with the same answer, you'd be partly correct. The problem is we now have to consider that our dice could be red or blue from the previous situation. And that leaves the other dice to be the other color. Whereas we did this for only one color orientation, if we had switched the colors, we'd have had twice as many options, or times two, which ends up being 6 out of 36, or 1/6. Now, if you really wanted to see that brute force wise, go ahead and build a table of all the different ways to roll a dice, where I have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And you can literally see there's going to be 36 options if I start making a table like this. This is horrible. These are not straight lines, I know. Just going to mark the ones that I want. So obviously, if I have a 4, if I have a 4 up for this dice and I have an odd number, which would be right here, and right here, or if I have a 4 with here, here, and here, we can see that I found 6 ways to do it. So I said, what suppose the top dice is a 4, and that means the side dice has to be an odd, and we just went down the list and we just wrote them out. You see there's 6 options out of the 36. On the other hand, if I had said the top dice, if we go back to the previous problem, the top dice was red and the side dice was blue, then all we get is this strip right here. And so you have to kind of pay attention to these problems very clearly, because is their ordering is a massive problem. And this is a problem even in cryptography, because we still use a lot of probability. In fact, probability is used a ton in today's world. I would recommend being very familiar with how probability works. Well, let me throw at you another option. Sorry about that. Hit the button. Let's just think about another alphabet soup. And I want you to try these 4 questions. You have 20 A's, 15 B's, and 10 C's in a container. Except this time, notice I'm going to pull one out and I'm going to put it right back in and select a letter. Now, what's the probability that A is the first letter and B is the second letter? So I gave you an order. That's kind of important. So go ahead and pause the video, figure out the answer to these 4 questions. All right, so let's go through this first one. Now, there's a way that we can do this, and we're going to talk about Bayesian statistics next week. I'm going to save that. I'm going to give you a little bit of Bayesian statistics. But the probability the first letter is an A is going to be the total number of letters, which if you add up real quickly is going to give me 45. And I have 20 A's. And I'm going to multiply, because for every single one of these situations, there is a situation that has a B in it. So it's the probability of having a 20. And so usually when there's and, we multiply, and or we add. Show you that doesn't always quite work, because it depends on what are we doing. But if the second letter is a B, well, that means that I'm pulling out 15 possibilities out of my 45. So I'm going to get 300 out of 45 squared. And that is going to be my probability that I get an A followed by a B. Now let's look at the first one. I mean, the next question, which is that an A and C, if I'm dealing with that, 2 letters are A and C. Well, let's consider that my first letter is an A. Because first we can say, let's consider this ordering, and then we'll do our second letter. And then we can undo our ordering by actually multiplying by it. Because we assumed an ordering, we have an ordering, and then we're actually going to undo our ordering. So if I did this one, I would have 20 out of 100 times 10 out of 100. That would be if I did AC. So this right here is for AC. What if I did CA? Well, guess what? It's the identical thing. And so it's going to be just double this. So I'm going to multiply this whole thing by 2, which equals, I'm just going to do the numbers real quick so you can kind of see that's going to end up giving me 400 out of 10,000. Now, real quick, when you're trying to figure this out to make sure you know you didn't screw it totally up, if you get a number that's bigger than 1, you messed up. There's impossible to have probability of 120%. It's not possible. You could have still get 120%, but it's just not likely. All right. On the other hand, so I'm going to have to clear all these drawings out. So you can kind of look, rewind the video if you need to. What if my first letter is a B and the second is also, meaning I pulled a B and then pulled a B? Well, in reality, that's going to be 15 out of 100 squared, which, let's see, that's 225 over 10,000. Sorry. I started doubting myself for some reason. So, and we can reduce this, obviously we reduce this fraction, but I'm just writing it so I can clearly see that it's not bigger than 1. And so the first letter, even though I said the first letter is B and the second letter is also, it's the same thing as this last one where we said the 2 letters are both C, because the ordering doesn't really matter, because the first letter is B and second letter is B. It's still the same thing as if it's first letter is B and second letter is B. It's still the same situation. So when the letters are different, as in problem 2, we have to multiply by 2. However, if they are identical, which means it was actually impossible to tell 2 situations apart, we don't have to worry about this. So the last one, the 2 letters are C, is just going to be very, very similar. And we're going to have simply 10 out of 100 squared, which by the way is 1 out of 100. I'm going to have 10 squared or 1 out of 100. And then we can start comparing all these probabilities and saying which one of these is smallest, which one of these is biggest, is most likely to happen. And that's why we care about probabilities, because we want to know what the probability of something is so we can then use it to figure out, is this likely or not likely? The closer a number is to 1 is likely. In fact, we usually don't say it's likely unless it's over like a 90%. If it's over 50%, it's better than likely, but not super likely. And that actually leads me to an interesting question. And this is one that I want you to kind of think about for a second. This is one I love to do with actual class in person. Imagine for a minute that I have 50 people in a room. What's the probability that at least 2 people have the same exact birthday? Now let's exclude the leap year. That throws things off. I know that's just nasty. I don't care about year. I only care about they have the exact same birthday. So like pick your date, April 12th. What's the probability they both have April 12th as their birthday? Well, this all actually comes down to the interesting part of how many birthdays are there. And the probability with this one is it's probably that at least 2 people have the same probability. What if 2 of the same 2, 3, 4? We have to conclude all those things. At least 2, the way we usually do this is, well, what's the probability that at least that less than that? So let's essentially what we're saying is that means one person, no one has the same birthday as someone else. So we're going to get rid of the 0 case and we're going to get rid of something else. So what's the probability that everyone in our room has at least the same birthday? Well, let's consider that. What's the probability that everyone has different birthdays? Because that would be essentially the same question. So if the probability of the same birthday, I should say that they all have different probability of different birthdays. Probability different birthdays. That is good. Let's think about it. So the first person has 365 choice possibilities they can have out of 365. I know they can only have one birthday, but they could pick all of them. The second person, so we're just going to pick birthdays essentially. The second person in the room, they would have 364 options. out of the 365 because they cannot have the same as the first person. Well, what about the next person? They would have 363 out of 365. And we keep this up until the last one, which is 365, but the numerator is going to be 365 minus 49 because this was, if you want to have 50 options, the first one was minus 0, and then we minus 1, so forth. So we've actually had minus 49, not minus 50. This is the number of ways to have different birthdays. Well, a way to do that, to write that, the denominator is obviously 365 to the 50th power. And the numerator, I could write this as 365 factorial, but I just want to drop 365 minus 50 factorial. Because that will get rid of everything of the next term that's not on the screen over here and on. So this is the number of ways that I really don't want that everyone have to have a different birthday. Well, what is this? So what's the probability that at least two have the same? And it turns out that's going to be 1 minus this number, 365 factorial over 365 to the 50th power times this 365 minus 50 factorial. Well, what is that? Well, you quickly grab a calculator and we find out that this is equal to. So again, if we throw that in a calculator, we quickly get that this is 0.97 037 or approximate. Well, that's approximately. I'm rounding off a few decimal places, or about 97%. So there's a crazy part. You may have thought to have 50 people in the room, you might have somewhere in the 20% range because you have 1/7 of the possible birthdays covered. But the truth is, if you have 50 people in the same room, you have over a 97% probability that two people share the same birthday. So this is one of those, is not no guarantee. There's still 3% probability that they don't. But that is actually how it's crazy cool. So a question that I'm going to ask to think about is what would happen if, how many people do we need just to have the 75% probability? Or what about 99%? How would you figure out that? Think about what strategy you would use and then explain what that number would be. All right, good luck. Let me know what questions you have and hope you're enjoying this week.